I want to talk about is the fact that hydrogens next to a carbonyl like that, just let me fix the lights here. Lighting, that's better. Okay, hydrogens next to a carbonyl like that are actually acidic. Now they're nowhere near as acidic as the hydrogen on the oxygen of an acid. But they are acidic. And if you treat a carbonyl compound with a base, with a sufficiently strong base, that's just represented in a generic form, what you get is removal of that, what you observe is removal of that proton, and you generate a substance called an enolate. And you can write a couple of resonance structures for the enolate. You can put the negative charge on the carbon, or you can put it on the hydrogen. Now, this business of forming an enolate, in the way that I told you, allows you to predict that if you treat an enolate with a source of protons, then the proton could be captured here, or it could be captured there. And so, let me write the two possibilities. That's called an enol. And you can also regenerate the original ketone. Now it turns out that the enol form readily converts itself into the ketone form. And in fact, they are generally in equilibrium, although usually the equilibrium lies right over on the ketone side. And this process of a hydrogen moving in this manner is called tautomerism. And these two are called tautomers. So there's a ketone tautomer and an enol tautomer. And the amount of the enol form is usually very, very small. So let me draw up a particular example. So if you have cyclohexanone, the amount of the enol tautomer is essentially negligible. And if you have acetone, the proportion is even lower. But there are certain types of carbonyl compound in which the proportion of the enol form is very, very high. And the compounds in which that happens are compounds in which the structure is such that the enol form is stabilized. And the most important type of compound that follows that behavior is the so-called alpha-beta dicarbonyl compound. Because if you have that compound, you get about 76% enol, and the rest is the carbonyl form. And the reason why you have so much enol form there is that the enol is stabilized by hydrogen bonding within the same molecule, by intramolecular hydrogen bonding. Now, what's the use of this information? How can we use the fact that carbonyl compounds can exist as an enol or as an enolate, and that the amount of carbonyl compound is usually much, much greater than the amount of the enol? That's just information that I've given you. How can we use it? Well, supposing you have an optically active substance in which the asymmetric carbon is next door to a ketone. So let's have a look at an example of that. Here we've got a substance that I've drawn as a single enantiomer. It's a single enantiomer, and you can see that the asymmetric carbon, the carbon attached to 4 different things, is right next door to a carbonyl. And so this carbon is attached to hydrogen, ethyl, and this carbonyl piece. Supposing you treat that with an acid or a base, what you will find is that you end up with the racemate. So you start with a single enantiomer, and you treat it with an acid or base, you end up with the racemate. Now, what's the use of knowing that sort of information, and how do you explain what's going on? Well, you explain what's going on by this business of generating an enol or an enolate, as I'll show you in a moment. What's the use of this information? Well, I can give you one use. Supposing you have an optically pure compound, and the asymmetric center is next to a carbonyl, and this stuff is a medicine. And the idea is that if you've got some disease, you're going to swallow a tablet of this stuff, and it'll go in your stomach. The stomach contains HCl. So, just by using the mechanism that I'll explain in a moment, for acid-catalyzed racemization, the compound could be racemized in the stomach. Maybe that one enantiomer cures you, and the other enantiomer has no effect or is harmful. So then it's trouble. So this is actually a rather important aspect of the chemistry of carbonyl compounds. So let me explain to you how it is that if you treat such a compound with base, and you start with a single enantiomer, you end up with a racemate. Well, let's do the base-induced racemization. If I allow the base to attack this hydrogen in the way that I've shown, what you'll get is that enolate. Now, one thing I should point out, in this enolate, this oxygen, as I've drawn it, is on the same side as that ethyl group. There's another enolate that's also formed in which the ethyl and the methyl are interchanged. But that doesn't matter. The point that I need to make is that this compound is not chiral. It doesn't have any asymmetric center. Doesn't have any carbon attached to 4 different things. And the mirror image of this structure is exactly the same as this structure. So you start off with a single enantiomer. That means that the mirror image is not superimposable upon this structure. And you generate an intermediate that's not chiral. And then you pick up a proton from, let us say, from the water. So the electrons come back, they come out here, and they regenerate base, but they also regenerate the starting ketone, except that now it's racemic. Now, why should it be racemic? Well, there's a fundamental law that you had in Chem 261 that tells you if you start with something that's not chiral, and you do a reaction on it, and the product is chiral, you will get a 50-50 mixture of the 2 enantiomers. And so you start here with something that is chiral, you generate from it something that is not chiral, that's the enolate, and then you generate something that is chiral. This is chiral. And so by that fundamental law, you have to get a racemate. In other words, a 50-50 mixture of the 2 enantiomers. Now I can explain that in a different way. Because this thing is flat and not chiral, as far as a proton is concerned, if it approaches from this side, it will see exactly the same things that it would see if it approaches from behind the ball. So the probability that the proton will approach from the front is the same as the probability that it will approach from behind the ball. If it approaches from the front, you get that. If it approaches from the back, you get this. And these two are the 2 enantiomers. And so it's easy to understand how if you have an asymmetric center next to a carbonyl, and you treat that compound with base, you're likely to get racemization. Now I said over here that if you treat this with base, you get racemization, but if you treat it with acid, you'll also get racemization. So what I want to do now is to explain to you how it is that if you treat such a compound with acid, the same overall change occurs. So you start with single enantiomer, and you get a racemate. Well, if I write it all out, then I'll have to write it again, and then it'll slow down and give you a chance to follow. Let me write down this single enantiomer again.
I know, but it's so good. They're pretty much done.
Now I'm going to put it into acid. And what happens is a lone pair on the oxygen is protonated. Then water attacks that hydrogen on the alpha position to give you, once again, a substance that is not chiral. This time it is the enol instead of the enolate. The enolate has the minus on the oxygen, the enol has hydrogen on the oxygen. So now once again we've got a substance that's not chiral, and we started off with a single enantiomer. Single enantiomer. And now this is going to be protonated. So let me draw protonated water. There it is. The lone pair will come along, and the enol will be protonated. And then water removes that proton, so you end up with the starting ketone accepting that now it is a racemate, for exactly the same reasons that I gave you when I told you how this happens under basic conditions. Because this material is not chiral, but the product that's formed, that's this one and this one, they are chiral. And by a fundamental law, you start with a non-chiral substance and you make it into a chiral compound, then the chiral compound has to be a racemate, because this proton can be picked up from in front of the board or from behind the board. If it's picked up from in front of the board, you get one enantiomer of the final product. If it's picked up from behind the board, you get the other enantiomer of the final product, and the probability that it will be picked up from the front is the same as the probability that it will be picked up from behind the board. So you get a 50-50 mixture of the two enantiomers, with methyl pointing towards you and hydrogen away, or with methyl pointing away from you and hydrogen towards you. So when you have a when you have an asymmetric center adjacent to a ketone carbonyl or an aldehyde carbonyl, and you treat such a compound with base or acid, you generally get racemization. Now I'm going to show you a little variant on this.
Because of the double bond.
Supposing you start off with this racemic ketone and you treat it not with sodium hydroxide in water, but with the corresponding deuterated species. You have heavy water, D2O. What will happen? Well, what will happen is that you'll get the enolate, but instead of picking up a proton, it will pick up deuterium. So that's a way of putting deuterium into that starting compound. And all these processes, the racemization or the incorporation of deuterium, they all go via the removal of hydrogen next door to the carbonyl and the formation either of an enolate or an enol, followed by reprotonation or deuteration at the position next door to what was the carbonyl carbon. They're all the same, but you can do various things with them. And what you ought to do is to do problem number 18.3, which is equal to 17.4 in the ninth edition. Now, why would one want to put a deuterium atom in some compound? Well, maybe you want to find out the metabolic fate of the compound. You know, if you take a medicine, the body does certain things to the compound, the active ingredient that's in the medicine. And sometimes it's very important to know what the body does to the compound, because maybe the body changes the compound to something that's very harmful to you. Then, of course, if you're working on the drug discovery and you find something that really cures some sort of bacterial infection, but you find that one of the metabolites of the compound is harmful in some other respect, then of course that potential medicine is useless. And so it is actually important to be able to follow the metabolism of various compounds, and one of the ways of doing that is to label the compound with various isotopes, sometimes deuterium, and then you find out what the products of the reaction, of the metabolism is. Then you feed it to rats. You take the urine from the rats and you try and isolate whatever is in there, and some of the material might have deuterium in it. And if you can work out the structure, then you can propose a mechanistic pathway of what's going on. Okay, so there's another use of this business of making enols and enolates. Supposing you want to put a halogen atom at a position next door to a carbonyl. And there are actually good reasons for wanting to do that, because the compounds that you generate in that way can be converted into all sorts of other substances. And it turns out that the way of putting a halogen in a molecule next door to a carbonyl involves the formation of an enol or an enolate. So let me show you how that works. Okay, I've got here, looks like some sort of bat, doesn't it? I've got here a symmetrical ketone. I've chosen it to be symmetrical for a special reason. I don't want to complicate matters by having to explain to you which side of the carbonyl is going to react. That's a little bit beyond this course. Because this is symmetrical, if I put a halogen here, or I put it there, it's exactly the same compound. So how does one do this? Well, what you do is you take the halogen, whatever it is, chlorine or bromine or iodine, and you treat it. You add the halogen and base or acid. And if you do that, what you will get is the alpha halo ketone. Alpha halo ketone. That's the alpha position, that's the beta position, that's the gamma position. Now, what's going on? How is it that the halogen gets there? Now, the only halogenation mechanism that you know so far from the course is the business of free radical halogenation. So when you see this reaction, one of the thoughts that might come to you is this a free radical process? The answer is no. It's an ionic process. And the way that it works is that the ketone is converted into either an enolate if you're using base, or an enol if you're using acid. And it's the enol or the enolate that reacts with the halide. So let's assume that it is let's assume that we're going to use base. So I've made the enolate. And let me just remind you again, some of you may wonder, why have I drawn this particular stereochemistry of enolate? Well, the other stereochemistries also form, not in equal amounts. I suspect this is the major stereochemistry. The stereochemistry of enolate doesn't matter. Doesn't matter for us. You just make an enolate. And now we're going to treat this enolate with, let us say, bromine. So the electrons come there, they come out onto the bromine. And you get now the alpha bromo ketone. Now, I realize that this is a new reaction for you, but it's actually not so new because you know from Chem 261 that if you have a double bond, it does react with bromine. And all this is a very highly polarized double bond because of this O minus, which is pushing electron density out this way, so that's what you get. So if you carry out a halogenation under basic conditions with a ketone, you get the alpha halo ketone. Now, of course, I'm sure you realize that this compound still has a hydrogen there. And so I could deprotonate it there to make another enolate, which would react again with bromine to give me a dibromo ketone. And then if I continue, I put a bromine here, and then a second bromine there, and eventually get a tetrabromo ketone. And indeed, that's exactly what happens. But the way to control that is to use only the calculated amount of bromine to put in one bromine. If you put in excess bromine, you're asking for trouble. You're going to get dibromides, tribromides, and tetrabromides, all via this enolate mechanism. Now, supposing you don't want to do the reaction under basic conditions, maybe something else in the molecule that you're dealing with, apart from the ketone, maybe there's something else there that's sensitive to base. Well, you can do the same thing by using an acid. And the mechanism is very, very similar, excepting that it does not go through an enolate. It goes through, as I'm sure you'll guess, it goes through the enol. So let's run through the mechanism of that. And again, don't make any conclusions as to the stereochemistry of the enol. This is a Z enol, I could very well have written the E enol. The stereochemistry doesn't matter. Now, what's going to happen? Well, what's going to happen is that if I use bromine, and then there will be some perhaps water or bromide ion, something that can act as a base to remove that final proton. And what I end up with again is 1, 2, 3, 1, 2, 3, so I'm going to rub one out. What I end up again is the alpha bromo ketone. And this just is exactly the same as the enolate one, except instead of an enolate, you use an enol. And because of that, you have to have an extra step at the end to remove the proton that is on that final oxygen. Now, it turns out that, well, two things. I said a moment ago that these alpha halo ketones are very useful because you can convert them into all sorts of other things, which in due course I will mention a few. That's one use. The other use is that this reaction, at least a certain form of it, has been used often as a diagnostic test for methyl ketones. Now, what do I mean by that? Supposing you've got some compound and you're asked to find out what it is. You know, maybe the police ask you, they've captured it in some criminal's house and they want to know if it's some banned substance. Now, these days what you do, there are all sorts of instrumental ways. You run an NMR spectrum, infrared spectrum, mass spectrum, and so on. But many years ago, those techniques weren't available. And supposing you started to suspect that this stuff was a ketone, perhaps with 2,4-dinitrophenylhydrazine, in the presence of acid, it gave a nice orangey red crystalline compound. But you wanted to find out if it was a methyl ketone. Maybe that was an important issue. Well, you use this reaction in order to do that.
I don't want to shine my face because I hate writing on the back when I write in pencil because it smudges. So I like doing it on one page. Yeah.
I write really big.
Are you running out of carbon paper?
No, I saw your message though. Just use it as scrap paper for later.
I was thinking that, or I could save some for like whoever next semester. Like maybe Carmen, because I know she is.
Supposing you've got a compound like the one I've shown there, which is a methyl ketone. It's also a phenyl ketone, but the point I need to make is that it is a methyl ketone. If you treat it with iodine and base, what happens is you get this compound called iodoform. And it's yellow, it's canary yellow. If you've never seen a canary, you want to find out what color it is. Next time you have a lamb, take a methyl ketone, treat it with alkaline iodine, and you'll then learn what color a canary is. Did I ever tell you the story about the Nobel Prize winner and the parrot? I don't think so. But this parrot's true. The Nobel Prize winner in California, who was a physicist, he was very well known in the local area. Then he was a pet store, wanted to buy a parrot. So the attendant showed him a beautiful parrot standing on a perch. And the Nobel Prize winner says, "How much is this?" And the pet store says, $2,000. The Nobel Prize winner raised his eyebrows, and the pet store owner said, "Well, it speaks 100 words." And then the physicist, that's what he was, saw another parrot, just as beautiful. And he asked the price, and it's $5,000. And he was a bit surprised. And the assistant said, "Oh, this parrot speaks 500 words." And then the physicist saw a scruffy old parrot on a stand in the back of the store. He said, "How much is that?" And the assistant said, $12,000. And the physicist said, "Well, how many words does it speak?" He said, "None." "Well, what do you mean? It costs much more than the others. It doesn't speak anything." The assistant said, "Ah, sir, that parrot thinks." That's a story with some variation.
So I can come back. I know it's going to be like, it's condemned.
But it was applied to a California Nobel Prize winner, Richard Feynman. Anyway, if you take a methyl,
so balance is gold.
some parrots are this color as well. If you take a methyl ketone and you treat it with sodium hydroxide and iodine, this is what you get. And I've just got enough time to show you how it works. What happens enolate, it reacts with iodine. So you get the monoiodide. And this gives you an enolate again, which reacts with iodine, which gives you then the diiodide. And that gives you the enolate again, because there's still a hydrogen here. It reacts with iodine to give you the triiodide. And now base comes in, attacks there. And this, you see, is a pretty reasonable leaving group in these circumstances, especially as probably this proton is also removed, so that actually what you get, I made a little mistake there, what you get is that. So wherever you have a methyl ketone, if you treat it with sodium hydroxide and iodine, you should get a yellow precipitate of iodoform. If you do the same thing with bromine, you'll get bromoform. And if you do the same thing with chlorine, you'll get chloroform. But the iodine one is crystalline, and it's the right colour, and so it's a chemical test for a methyl ketone. Or you should all remember that this Thursday, that's tomorrow, at 5:30 in here, we'll have the makeup lecture. Thank you very much.